In this example, I'm going to describe how to use Mathematica to construct a small simulation of what's called the two-dimensional Ising model. Now I should say Mathematica is not an efficient way to do simulations. This is only for illustrative purposes, but it does give a little indication about how to program in Mathematica, and as well it can be useful to do small simulations just to kind of prototype things in Mathematica. So this example has certain things that recommend it, but as I say, I would not recommend ever doing any large-scale simulations in Mathematica. So what is the Ising model? Well, it's a very simple model that is meant to be an idealization of magnetic interactions, for example, between neighboring magnetic moments in a crystal, but it also can be thought of as describing the interactions of two species in a binary mixture and many other sorts of circumstances. So this is not a very pretty regular lattice, but let's pretend that this is a nice regular lattice. And each cell in this lattice contains either an up spin or a down spin. Which you could also think of as an A or a B or a plus or a minus, or what have you. And the energy as a function of the coordinates, and the coordinates here are these S sub I, which are either up or down, or let's say either plus or minus 1. The Hamiltonian, the energy as a function of those coordinates, is the sum over pairs of the product Si, Sj. And by pairs I mean near neighbor pairs. That is, this spin right here interacts with this one, this one, this one, and that one. Nearest neighbors on the square lattice, that's the rule. So if they are, minus Si, Sj. So that if they are both pointing the same direction, that contributes minus 1 to the energy, and if they are pointing in opposite directions, it contributes plus 1 to the energy. So if you cool this system, it wants to align all the spins, and if you heat it up to a high temperature at which entropy is dominant, then the spins randomize. And this model has, in fact, a phase transition between a finite tendency for the spins to order and for a zero average spin. So the simulation that we're going to talk about is what's called a Monte Carlo simulation. And it's the very simplest sort of Monte Carlo simulation that you can imagine to explore the ensemble of different configurations of this system. And it's called a single spin flip simulation, in which you choose a spin at random, and then you compute the change in the energy that would occur if that spin were to flip, just by considering what are the interactions of that spin with its neighbors now, and what would the interaction be if you flipped it. And what you can pretty easily persuade yourself is the change in energy is going to be minus 2 times the spin that you try to flip times the sum over the neighbors of their values. Because if it's favorable now and you flip it, it's going to cost you 2. Now, because you go from -1 to 1 on that bond, and so this is the sum over the different bonds that that spin has, and so that's the energy change. Whereas if it was unfavorable now, then you'll gain 2. You go from a +1 contribution to the energy to a -1 contribution. Anyway, so you compute the change in the energy, and then the Monte Carlo, the Metropolis rule for accepting the flip is if delta E is less than 0, in other words, it's downhill in the energy, then you accept it with probability 1, and if it's uphill, then you accept with probability e to the minus beta delta E, where beta is the inverse temperature, 1 over kT. It's beyond my purpose here to explain why that's a sensible rule for exploring the ensemble of configurations, but it is. And so what we want to do is implement a little simulation that does this, that starts from some initial configuration, that proposes a bunch of random spin flips and accepts them, and therefore evolves the system forward so that we can see what it does under the action of many, many spin flips. So this is surprisingly easy to do in Mathematica. The first thing we need is some place to store the spins. So we're going to have an n by n array of integer values, which will be randomly, which will be called s, and will be plus or minus 1. And we're going to have a function dE of I and j, which will be the change in energy on flipping spin at I, comma j in the array. And then we're going to have a thing called MC step, which will be a function of beta, which will choose a spin at random and try to flip it by the Metropolis rule. And then we're going to have something which draws the matrix to draw the array showing the up and down spins. Those are the 4 functions that we want. Okay. We're going to let the variable s, which is, as I say, a two-dimensional array of variables, of plus and minus 1, be a global variable, and we're going to let the size of the array also be global. So we'll just start out by saying, well, we need a function to initialize s. I didn't mention that. And we're going to initialize it to random choices of plus 1 and minus 1. So the initial condition function will just be to say S is an array of 2 so we'll just start out by saying n is going to be 100. And then the initial condition function will be to set S to be an array of this function, an n by n array of that, and what that function is, well, random integer gives either a 0 or 1, as in flipping a coin, and then 2 times that minus 1 will give me a plus 1 or a minus 1. And then the energy function dE will be minus 2 times spin at I and j times the sum of its neighbors, and at this point we have to think a little bit, because if we're in the middle, that's fine, but if we're at the edge and we take the right-hand neighbor of the spin, then what do we mean? What's over there? You know, is there a boundary spin, or what do we do about those terms? So one thing we can do is to impose periodic boundary conditions, so that this spin's right-hand neighbor right here is actually a copy of this spin, as if there were a whole nother copy of the very same lattice right over here, and that spin there was just copied here, and likewise the left-hand neighbor of this spin would be that one, because there was a whole nother copy of the array over here, and so this thing's left-hand neighbor is actually that spin, and so forth. Okay? So a way of implementing that is to we would run off the map, you see, if j got to be equal to n here, and then we took j plus 1, what would we do? So there's a nice function called mod, which takes is the modulo function of integers. In other words, if I take the mod of any of these integers mod 3, well, you'll find out it maps it, into 0, 1, 2, 0, 1, 2, 0, 1, 2, right? We would like a mod function that actually maps the thing into 1 through n, not 0 through n minus 1, and that you can do with an offset of 1. So then you'll see that what the mod function, so this is the thing we're taking the mod of, which in my little example here is a list. Here's the base we're doing the mod with respect to, and here's the offset. And you see the effect of an offset of 1 is, instead of mapping into 0, 1, 2, 0, 1, 2, it maps it into 1, 2, 3, 1, 2, 3. So basically the mod function subtracts however many 3's, or whatever the base is, to make the number, which is its argument, land in the range that starts with this thing. Okay. So what all that means is that we want to wrap any of these shifted arguments in mod n with offset 1, and that will protect them from going off of the board. And now our DE function is fine. Okay. To draw the matrix, we want to draw it by drawing a bunch of squares. In fact, a table of squares, and we choose the color of those squares to be depending on the ij value, depending on the spin value that sits at that ij entry, and so this hue choice turns out to be good. And then we draw a little square explicitly that goes from ij to I plus 1 j to I plus 1 j plus 1 to I j plus 1. So those are the borders. The polygon function draws a little thing that has those as its corners, and then this table gets its goes from 1 to n in both I and j, like that. The drawing function takes a little while because you've got 10,000 squares to draw. And there they are, all randomly chosen as the initial condition would have it. Okay, so now we've got everything except the thing that does the Monte Carlo itself. And as I said, that's a function of beta. And we need to choose a random spin to flip, so we need to choose an I and a j randomly between 1 and n. And that's how you do that. Okay, so that will choose me a random integer between 1 and n. We compute the energy difference, which I'm going to call dE val. And then we've got to decide whether we're going to flip the spin. And so the way we do that is we compute a Boolean variable, that is a logical variable, 0 or 1, called success. And success is, well, if the energy change is less than 0, then success is certainly true. But if the energy change is bigger than 0, then what we need is instead to go and accept the thing anyway with probability e to the minus beta e. The way that you accept it with probability e to the minus beta e is you generate a random real number and you ask whether that random real number is smaller than e to the minus beta e, e to the minus beta delta e. So this term here will evaluate to true or false depending on whether the random real you choose happens to be less than e to the minus beta e or not. And suppose this was a fourth. Okay, well then the random real will 1/4 of the time be smaller than that because it's in the range 0 to 1, and so 1/4 of the time that's going to come up true anyway, even though the energy difference was positive. So that's how you choose your success value, and then if you succeeded, you go ahead and flip the spin, which we can just do by multiplying it by -1. And that's a Monte Carlo step. Now I realized I made a sign mistake back here in writing down the energy change, because actually if Si and Sj were all the same between it and its neighbors, then my energy change is certainly going to be positive because I'm going to flip from a negative value to a positive value. Every one of those bonds is happy, is giving a -1 to the energy now, and it'll give a +1 when I flip, and so the energy change will be 2Si Sj, not minus that. So I'll go fix this and evaluate that again, and now I should be able to run this thing. And so to run it, I just do the Monte Carlo step a bunch of times with some value of beta, which I've just chosen 1 arbitrarily. And then I can draw my matrix again to see how it changed. And again, this takes a little while, mainly because of the drawing. Okay, and let's just run it again, because 5,000 steps is not very many. And see what happens. See if it stops changing, or if it's, well, it seems to be getting a little coarser. Things are kind of gathering together, the up spins and the down spins. As I say, this is a slow way to do simulations, but it does allow you to get your hands dirty with how the simulation actually works, and also to play around with new ideas that you have for simulating non-standard things, and serves as a little example for how you go about programming in Mathematica.